This is section 4.6. We're going to be discussing a new method known as variation of parameters. So for this, we're going to let y1 and y2 be two linearly independent solutions to the homogeneous equation a y double prime plus b y prime plus c y equals 0. Now we've learned from before that the general solution to this homogeneous equation would be represented as such. Y, we put a little sub h here to differentiate it from other things that we've called y. So the homogeneous solution y, the generalized one, is equal to some constant times y1 plus some constant times y2. So y1 is a solution, y2 is a solution, but a more general solution is some linear combination of them where there are constants multiplied by them that we don't even know they can be anything. To find a particular solution to the non-homogeneous version, where we set it equal to f of t, some function, instead of 0, that's where this new variation of parameters is going to come in. And it dictates that we're going to replace the constants, the c1 and the c2, by functions. v1 of t, so that's just some function of t, and v2 of t, some other function of t. Now, we're going to impose some rules on these functions v1 and v2. Particularly to simplify future differentiation, we will impose a rule that v1 prime y1 plus v2 prime y2 is equal to 0. And you'll see how that simplifies things for us. So now let's get to work. We have that y sub p, which is going to be our variation of parameters solution to the non-homogeneous version of the equation. Yp is equal to, exactly as we defined it, v1 y1 plus v2 y2. Now, if we take the derivative, that's just going to be a couple of product rules, so we can see how that arises simply enough. But here's where the things that equal 0 come from. We have this v1 prime y1, that's right here. And if we add that to v2 prime y2, that's this one, we get 0. So that's simplified nicely for us. So we're just down to the derivative of yp is equal to v1 y1 prime plus v2 y2 prime. And now that we have fewer terms, that will make it easier to take another derivative. And again, this is just two product rules, but nothing's going to simplify here. We're content with this as a final answer for y double prime. We now substitute these values into the non-homogeneous equation ay double prime plus by prime plus cy equals f of t. So when I scroll down, we're going to see a rather large equation, but just note that we're substituting in this y double prime into here, this y prime into here, and this y into here. That's what we're going to see right here. But now we've assumed a few other things, if you recall. We assumed that y1 is a solution to ay double prime plus by prime plus cy equals 0. So after we simplify this and move the pieces around so that everything is where we want it to be, we factored out a v1 from something that is just equal to 0. And we have the same thing for y2, because y2 was defined to be another solution of the homogeneous equation. So they just become zeros. So we're left with f is equal to a times v1 prime y1 prime plus v2 prime y2 prime. And now we're just going to divide both sides by a, and we're going to get this final version of the equation. What we've accomplished here is we found our two restrictions on our functions, v1 of t and v2 of t. It says here, our goal is to find functions v1 of t and v2 of t such that this thing that we just solved for, f over a, must be equal to v1 prime y1 prime plus v2 prime y2 prime. but also the original restriction that we imposed. v1 prime y1 plus v2 prime y2 is equal to 0. Now, if we solve this system of linear equations, because that's all this is, two equations with two variables, that being the v1 prime and the v2 prime, we can solve for v1 prime and v2 prime. Now, this bracketed expression in the denominator is known as the Wronskian, and we'll see more of that later. But it's important to note that it is never equal to 0 by Lemma 1, page 160. So you can read that if you'd like to be familiarized with that. But if we integrate both of these equations, then we solve for v1 and v2. And those are the only pieces we were missing from our final generalized solution. So let's try this out. Find a general solution for the second derivative of y with respect to t minus 4y is equal to 4e to the 2t. Now, what you've certainly learned from this chapter is you always start with the auxiliary equation. The auxiliary equation is r squared minus 4 equals 0. So we get two solutions, plus or minus 2. Now, in the instance of homogeneous equations, if you think back to section 4.2, this is fairly simple, and we're done. We have our two solutions. y1 is equal to e to the 2t, because remember, generally solutions to homogeneous equations take the form e to the rt. So as soon as you solve the auxiliary equation, you have the only missing piece of information, and you're done. So we have two solutions. y1 equals e to the 2t, and y2 is equal to e to the negative 2t. But now we want to use our variation of parameters to solve the non-homogeneous version of this equation. And if we scroll back up to what the question was asking, this is non-homogeneous. It's not equal to 0, it's equal to 4e to the 2t. So this is the equation we're working with now. But we know some things about v1 and v2. Those are our two restrictions that we imposed on it from our variation of parameters. So here they are. We've got our y1, which is just e to the 2t times v1 prime, plus our y2 times v2 prime. And that added together has to be equal to 0. But also we have the derivative of y1, and this is the derivative of y2. And if you recall, this equation is set to f over a. Well, we don't actually have an a term. I'll scroll up to show you what I mean. A is the thing that's multiplied by the second derivative. It's just 1. So we're just going to have f over a is equal to f. So on the right side of our equation, it should say 4e to the 2t. And that's what it says. So these are our two equations we're going to work with. Now, I'm going to take this top equation, and I'm going to isolate v1 prime. So I get an equation for v1 prime. Side note, we have this e to the negative 2t in the numerator and e to the 2t in the denominator. And you recall, if they have the same base, when you're dividing, you can just subtract the exponents. So negative 2 minus 2 is where that negative 4 is coming from. Now, we're going to take this information about v1 prime, and we're going to plug it into this equation. So we get 2e to the 2t times what we just solved for v1 prime, minus 2e to the negative 2t times v2 prime is equal to 4e to the 2t. And now we're going to be able to reach a solution for v2 prime if we can isolate it. So we're going to expand this, and then we are going to try to get that v2 prime all alone. And what you'll notice is when I divide both sides by negative 4e to the negative 2t, well, those 4 divided by negative 4, that just becomes negative 1. And e to the 2t minus a negative e to the 2t, it's just going to become 4t. 2 minus negative 2 equals 4 for that exponent. So we get v2 prime is equal to negative e to the 4t. I can take that information and plug it into my other equation to figure out what v1 prime is equal to. And that's exactly what I do. Negative e to the negative 4t times negative e to the 4t. Well, two negatives cancel. And when you add, because when you're multiplying exponents with the same bases, you just add the exponents. 4 minus 4 is 0. So we just get 1. Everything kind of canceled out there. So v1 prime is equal to 1, and v2 prime is equal to negative e to the 4t. Now to finish this off, all we need to do is integrate those two. So the integral of 1 is just t plus c1. And the integral of negative e to the 4t, there should be a little dt there, is negative 1 over 4 e to the 4t plus c2. So now this is kind of our final solution. We have our y1 and our y2, and now we're going to plug in our v1 and our v2. And the final steps are just going to be me trying to simplify it a little bit, where I wanted to have this e to the 2t factored out, although it's arguable what the most simple version of this solution is. But it's an explicit general solution. We've got c1 and c2 that can be any constant, and we've got the y value isolated on the left. Now we'll do another example. Find a particular solution. Recall that this solution is general, so we're going to do a particular solution. This is going to be an initial value problem for this equation, where y of 0 is equal to 0 and y prime of 0 is equal to 1. So first step is always auxiliary equation. R squared plus 3r plus 2 is equal to 0. That factors nicely as just r plus 1 times r plus 2. So we get our two solutions. R is equal to negative 1 and negative 2. And this is exactly what our final solution would be in section 4.2, where we're just looking at the homogeneous equations. We would have, well, this would have been a constant, but now we're doing variation of parameters. It would have just been constant times e to the negative t. That negative 1 comes from here, plus some constant times e to the negative 2t, where that negative 2 comes from here. But we're not dealing with constants anymore. We're dealing with these new v functions that are going to be able to solve any non-homogeneous version of the equation. Now, again, I'll scroll up. One of our equations that we deal with these v's has that f over a term. Well, this is your f. And once again, we have an example where a is just equal to 1. But remember that if there was something multiplied by y double prime there, it would have to be divided by f before placing it in this equation. But since a is just equal to 1, this is just f. So these are our two restrictive equations, and we're going to follow the exact same steps as before. We're going to take this first equation, and we're going to isolate v1 prime. And then we're going to take that value and plug it in to the second equation. Now we're going to multiply this through, and we're going to combine like terms, and we're going to try to isolate that v2 prime. Notice here I have negative 3e to the negative 2t, and I'm dividing both sides by negative e to the negative 2t. Well, those negatives cancel out, those e to the negative 2t's cancel out, all that's left is 3. So I get v2 prime is equal to 3, and I plug that value back in to solve for v1 prime. So I get that v1 prime is negative 3 e to the negative t. So I have my values for v1 prime and v2 prime. And now I'm going to integrate them. The integral of negative 3e to the negative t, that's this one, is going to give me 3e to the negative t plus some constant c1. And the integral of v2 prime is just the integral of 3 dt, which gives me 3t plus c2. We're going to plug these values back in to our equation that we solved for as v1 and v2. Remember, we've already solved for y1 and y2. And that is our solution. We are going to try to simplify it a bit because we've got some values we need to plug in for our initial value problem. So we're going to clean it up as best we can. So we're going to multiply it through, and we get this expanded form. And then we're going to factor out that e to the negative 2t. And hopefully that just makes things a little bit easier. So now when we plug in that when t equals 0, y equals 0, this is just a 1 on the outside that's going to be multiplied, so we can ignore that. This disappears because we're multiplying by 0, and this disappears because we're multiplying by 1. So all that remains is 3 plus c2 plus c1. So c1 is equal to negative 3 minus c2. This is just like doing any old initial value problem that we have in this course. Now we need to calculate y prime. So y prime, there's nothing too difficult here, but you will have to do a product rule when you take this derivative here. The derivative of 3t e to the negative 2t is going to have a couple pieces. But other than that, it's just a little bit of chain rule to get y prime. And then once you have y prime, you can plug in the fact that when t equals 0, y prime equals 1. That was part of the initial value problem. So we just plug in all these t's as being zeros. And we're left with 1 is equal to negative 6 minus c1 plus 3 minus 2c2. But we know what c1 is equal to. We can plug that in. And now, rather nicely, we have a positive 3 here, negative 3 is positive 3, and that's going to cancel out with this negative 6. So all of those just gone. And we're left with 1 is equal to negative c2. Well, that's clearly not right. No, it is. Okay, good. Because this negative 3 may be gone, but this negative times this negative actually turns this c2 into a positive. So this positive c2 minus this 2c2 does make minus c2. Good. So now c2 is equal to negative 1. c1, well, we got to bring that equation all the way down here and plug in that c2 is equal to negative 1. And we get that c1 is equal to negative 2. So finally, we can plug those values in. Y, as it is written right here in its simplified form, we can just plug in what c2 and c1 are equal to get this. And then we just combine the 3 and the negative 1, and we get 2. And this is our final answer. Y is equal to e to the negative 2t times 2 plus 3t plus 2e to the t. And that is the solution, not just a general solution, is the particular solution when we know that the points t equals 0, y equals 0 exist, and t equals 0, y prime equals 1 exist.